Welcome back to Honors Calculus. In this video, we're going to be looking at implicit differentiation. The actual application of the mathematics that we're looking at here is fairly straightforward. There's not a lot that we're going to have to really worry about. But the vocabulary and the situations that lead us to that mathematics can sometimes be convoluted. So let me get my head out of the way and let's look at a relatively straightforward example. We know that a graph is a function if it satisfies the vertical line test. And if the graph does not satisfy the vertical line test, then it is not a function. As an example, let's take a look at x squared over 25 plus y squared over 16 equals 1. This is the graph of an ellipse. If you're not familiar with graphs of the conic sections and how to identify the graphs, it's not that big of a deal. You don't need to necessarily be able to analyze this graph from the equation, but it is an ellipse, and if you're familiar with that, then you can gain a little bit of insight in what we're doing. Now let's try to draw some axes that are large enough that we can actually fit everything we need to on the axis without too much issue. Specifically to graph an ellipse, it's x squared over a squared. 25 is 5 squared. So if we go out to 5, 0, and we go to negative 5, 0, that will give us the constraints in the x direction. And it's y squared over b squared. B squared is 16, so b is plus or minus 4. Go out to 0, 4, and to 0, negative 4, and plot those points as well. Play a nice game of connect the dots. Try to draw things that look like smooth curves. Fail badly at it and pretend anyway. And you have the picture of the ellipse. Clearly, this is not a function, right? It fails the vertical line test at every point except for the left and right endpoint. But if we know, for example, that we want the top branch, we can consider the function while y is positive. Or if we knew that we wanted the bottom branch, we could consider the function which assumes that y is negative. That's what I mean when I say an implicit function. Or if you prefer algebraically, I can rearrange this equation. And we can write the same equation as y equals plus or minus 4 times the square root of 1 minus x squared over 25. If I choose the plus branch, then I am implicitly defining the function that I graphed in blue. If I choose the minus graph, then I am implicitly defining y using the function that I graphed in red. So this curve gives me two functions. And any curve that is not actually satisfying the function rule, we can find a way to split it, take just part of the curve, and that part of a curve defines a function. y prime of x may not make sense when we're thinking about a function implicitly like this. But the fraction dy dx still can make sense. That's still the slope of the line tangent to the curve at the point. And just because the curve isn't a function doesn't mean that we stop having tangent lines. So even though that y prime of x doesn't make sense, that's still going to be the tool that we use here. So if I rewrite my equation, x squared over 25 plus y squared over 16 is equal to 1. I'm going to think of y as a function of x. I know that y is not a function of x on the entire curve, but I can pretend that y is a function of x by just making a mental note that I'm going to restrict where I'm looking so that I'm only looking at a part of a graph where it is a curve. And if I have done that, well, that completely failed. Let's do it the hard way. Right. Once I have done that, I can differentiate both sides of the equation. It's perfectly valid for me to do that. I can split up the derivative over the addition. I can take out the constants. And I can differentiate all of these things. The first derivative is fairly simple. The derivative of x squared is 2x. Multiply that by 1 over 25. Let's write this out in detail for this one. Right, 1 over 25 times 2x. On the right-hand side, that's also very easy. The derivative of 1 is 0. That last one I saved for last because that's where the confusion happens. It's not difficult, it's nothing new, but it looks scary. To take the derivative of a function being squared, we have a function acting on a function here, right? This is the chain of the squaring function of y of x. So we take the derivative of the squaring function, which is 2 times the stuff inside. And then we use the chain rule to multiply by the derivative of the stuff inside. The derivative of y of x is y prime of x. Then to actually find the derivative, we can rearrange and solve this equation for y prime. You notice at this point I'm suppressing all of the of x's because it's not really a function of x, and calling it a function of x is misleading. All right, here's why I never reduced anything, because those factors of 2 cancel each other out very nicely at that step. I guess one more step from here. Again, thinking about this in terms of y prime, probably still misleading. So I'll take one more step, and I'm going to write this thing as dy over dx. Again, y prime dy over dx, that's two different notations that we've talked about for the derivative. They mean the same thing. There's no real reason that one or the other is better. But with that tool, we can now find the derivative. And from here, we have all the tools we can use. When you are looking at an implicitly defined function, it's generally going to be the case that the derivative is going to depend on both x and y. And that makes sense if I go back and I look at the picture. Get my head out of the way so we can actually see the picture. Actually, no, I need to point at the picture, so let me come over here. Right? We know that when y is positive, I can't see what I'm doing in gesture at the same time, and when y is negative, we get two different parts of the curve. So I need to know whether I'm dealing with the part of the curve that's talking about a positive y or the part that's talking about a negative y, in addition to knowing the x coordinate, in order to figure out which part of the curve I'm on, to figure out whether I'm looking for a tangent line that's going to look like that, or a tangent line that's going to look like that. So that's why it's not a surprise that our final result here has both x and y in the expression for finding the derivative. Later on, we will look at some applications. We'll find some tangent lines. We'll even take some second derivatives. But for right now, I just want to get used to this process of thinking about y implicitly as a function of x and using that in order to differentiate. So in this particular case, we have y cubed plus y squared minus 5y minus x squared equals -4. Sometimes I write that as minus x squared plus 4 equals 0, but you know, doesn't make that much of a difference. Um, the graph of this curve ends up looking something like that. That was terrible. Let me try that again. Yeah, something kind of like that. I think of it as a graph of a cauldron, but whatever you want to think of it as. It doesn't really matter. The thing that matters is that it very clearly fails the vertical line test in these couple of regions. So y is not a function of x. You cannot solve this equation for y. But if we're lucky, we'll be able to differentiate. And the derivative is always going to be linear with respect to y prime. And so we will always be able to solve that and find an expression for y prime. All right, so we'll differentiate implicitly. I'm not going to go through and write all of the y's as of x this time because I want you to get used to writing this out without that. But I am going to take the time to write out the step here where I'm announcing that the thing I'm doing is taking the derivative with respect to x. Because that actually does make a difference. And seeing that, at least for me, always helps me remember that when I want to take the derivative of y cubed, well, the derivative of something cubed is 3 times that thing squared. But then because it's the derivative with respect to x and the thing I'm differentiating is not itself x, I need to multiply by the derivative of y. And the derivative of y is y prime. Likewise, the derivative of something squared is 2 times that thing, but because that thing is not x, I need to use the chain rule and multiply by the derivative of y, which is again y prime. Then I have the derivative of y, which is y prime. I have the derivative of x squared, which is minus 2x. And this time I am differentiating x squared with respect to x, so I don't have to use the chain rule here. And then finally, on the right-hand side, the derivative of a constant is 0. Notice that several of these terms have a y prime in them. Every time y prime appears, it is by itself. It's not being squared, it's not being square rooted, it's never showing up in the denominator. You have some mess multiplied times y prime. And so I can factor all that stuff out. I can move the 2x to the other side of the equation, and I can divide to get a nice result here. All right. So here's one more problem. I have x times the cosine of y is equal to, I wrote that backwards, I apologize. Let's try writing this correctly. X times the cosine of y is equal to y squared. This one's a little bit more challenging to differentiate. Notice that we have x times cosine of y. That is a product of two things. We'll need to use the product rule. But thinking about that, see what you can do differentiating this one, and then rearrange to find an expression for y prime. All right, see what you can do with that one. I'll see you in the next video.